is Duncan here, is going to talk a bit about actually securing how we distribute our packages ourselves, and then we have a talk from FP Complete on various ways of signing packages. So we'll start off with Duncan, and then we'll go from there.
Thank you very much. Okay, yes. So, security. Often starts off rather fuzzy. What do we mean? What do we want? We want a sort of warm, fuzzy glow. Why do we want security? Well, I mean, it's kind of obvious. And it's become sort of more and more important over time. You know, the companies really want it. You know, people have come to me and said, look, eventually my management are going to say, you know, what are we doing with security? You can kind of get away with it for a long time, but you know, we want to sort of do something before it's too late, before we all get compromised and it all looks bad. But we want to be precise about what we mean, because otherwise this stuff becomes very, very fuzzy. So I want to start initially by talking about, that kind of fuzziness and trying to pin that down a bit. So what sort of things might we want? What do we mean intuitively by security here? There's various sort of things we could mean. We could mean that the packages are not modified between the server and you downloading them, or between an author and you as a user. Or you might mean that you want your packages to be written by people that you trust. Think like a classic GPG cloud of web of trust kind of thing. And there's obviously things we need to keep in mind when we want to build a security system. There's a trade-off always between convenience and how much security you can get. In the case of hackage, we don't really want to raise the barrier too much for contribution, right? One of the really good things about hackage is that you can host your code anywhere you like. It's just a distribution point, right? It doesn't place too many constraints on how you do things. So in particular, we don't want to force everybody to sign everything. Right? That would be raising the barrier too high. We might like to make that a thing that you could do, but we don't necessarily want to say that is something that you must do, because that's raising the barrier to entry. And we want to, hackage and package distribution in Haskell has been successful partly because the barrier is actually quite low. Other things to keep in mind is that mirrors are really useful. I mean, that's the classic way to improve robustness is having mirrors. And trusting mirror operators and CDNs isn't great. It greatly increases the size of your sort of trusted base, if you like. So those are sort of things to keep in mind as we're sort of starting to think about security. What do we want exactly? Now, everybody knows, although people still get it wrong, that you should not write your own crypto algorithms and your own crypto protocols. You should leave that to the experts, right? We all know that. But sort of going one level higher, system design, that reusing existing protocols and existing crypto algorithms, whatever, that is also still hard. There's lots of difficult, subtle details. It's very easy to miss details, things that you simply weren't aware of. I don't claim to be an expert on this, and most of the rest of you here are not either. And we have to have a degree of humility about that. And if you look on like the Linux Weekly News security page every week, you'll find dozens and dozens of examples throughout our industry where people have just done this really badly. You don't need to go very far to find examples. One particular example, Docker had a system for verifying images that you download, except that it was totally broken. They're actually incidentally now using Tough, which is what I'm about to talk about. So the conclusion from all this initial stuff is that, yes, crypto algorithms and protocols leave that to the experts, but also, if possible, leave the architecture of a security system to experts, if you can get away with it. If there's a system that you can copy or use, do it. So that's what we have been doing. We're using this design by existing experts called Tough, the update framework, which I will talk more about in a second. But before we get there, let's play the game of let's come up with the first thing we thought of and see why it doesn't work. Right? So Tough explains why a whole bunch of things don't work. In that they've got a bunch of papers, but let's sort of go through it together, and you'll see. This, I came up with one of these as well, and if I'd done the first thing I thought of, it would have had all of these flaws. So let's have a look. So, obvious approaches. If I went around a room, I bet 3/4 of you would come up with one of these three things. So this is authors signing packages, like think classic GPG signing, the server signing some manifest of all the packages that are available, or the server using HTTPS. Those are sort of the classic things that you'd think of. So let's be a little bit more precise so that we can talk about what later on we'll be able to see what attacks work and don't work against this. So with authors signing packages, we're going to say that authors sign packages in tarballs individually, right? You have a tar.gz and you've got a tar.gz dot whatever GPG signature. Authors manage their own keys, and there is some mechanism, which I'm leaving slightly fuzzy because there's actually quite a lot of detail to work out there, some mechanism for the client to decide which keys they're going to actually trust. But you could imagine something like saying, here is a set of keys of all the authors I reckon are okay, and I'll trust anything written by those guys. Would be a sort of first go, perhaps. If you're signing a manifest, how does that work? Well, this most straightforward thing is you say, we've got this list of all the tarballs, their names and their hashes, like cryptographic hashes, SHA, whatever. Then that manifest itself is signed by some key that's held on a server, and the clients trust that server key, and so they therefore can verify the content of any tarball they download. And then HTTPS, fairly straightforward. So those are the systems. Let's first think of the obvious advantages and disadvantages that we can all see, and then we'll turn to the literature. So if you have authors signing packages, well, that's extra work for the authors. If we are not raising the barrier and saying that everyone has to sign their packages, then obviously there's no protection for packages that are not signed. In practice, I would guess that we would be doing very well if we managed to get more than half of all the packages on Hackage signed by authors. The obvious advantage of author signing is that it's end-to-end, right? The author signs it, and the client verifies it, and doesn't matter sort of what happens in the middle. That's the sort of the big selling point for that approach. Although you need to be quite careful about how you decide which keys to trust, which author's keys to trust, right? That's a sort of fuzzy point. If you have a server signing a manifest, well, that's nice. There's no extra work for the authors. It's sort of fully automatic. It covers every single package, and that's great. But there's no protection in the case that the server itself is compromised. If you're using HTTPS, again, there's no protection in case the server is compromised. But you also have a problem with mirroring. You either have to trust your mirrors, or you just can't use mirrors. And neither are really great. Since mirrors are the best way to make things reliable. Even Amazon S3 goes down from time to time. Okay, let's turn to the literature. So this is a paper, well, a number of papers by the tough authors, and one of them looks at attacks on existing package managers and package management systems. So we're going to go through. I'll go through briefly what all these are. But what you have to imagine is that you control, say the Wi-Fi, or you control the network or a mirror between the server and the users, the clients. Okay. So this is the first thing that we're all thinking of is changing one of the tarballs, right? And so author signing or manifest signing ought to deal with that. So that's the sort of most obvious attack. But there's others. So rollback. This is where an attacker supplies genuine packages or sets of packages, but they were older ones that were signed 6 months ago and might have lots of versions of software that is now known to be vulnerable. So that's bad. Freeze attack is similar, but it's where the attacker in between doesn't let the client make any progress. They're not being forced to roll back to an earlier one, but they are unaware of updates that are now available. Mix and match is where an attacker is able to supply, without the client noticing, obviously, combinations of packages which never existed upstream. And that's slightly more subtle as to how that could be a problem, but it means that you might be able to have combinations of software which are vulnerable together where they were not vulnerable in the sets that they were originally. So it's a slightly more subtle one. You might be able to sneak in extra dependencies. If you've got metadata that is being passed separately from say, tarballs, if you could change that metadata, you might be able to trick clients into installing extra, evil 1.0 as a dependency of the thing that they're installing, right? And that would be bad. You could have an attack where a legitimate author, someone who does have a GPG key or whatever, and they are allowed to upload some packages, goes and uploads some other package. We can all think of examples where well-meaning people might want to go and make a bug fix to base or something, but we might want to make sure that they can't do that. And in particular, we want to be able to stop attackers deliberately trying to do that. After all, anyone is allowed to sign up and publish packages on Hackage. Everyone is a legitimate author, but that doesn't mean that everyone ought to be able to upload any package, right? Okay, and then we've got these two about downloads. Endless downloads is where some intermediate server just supplies you with an endless stream of data, and your download, your update never finishes. Now this, importantly, never finishes without you noticing. So this is partly a kind of user interface issue. If you think about software systems that do updates in the background, if the update in the background never finishes, that's effectively, it never updates, right? And slow download is kind of the same. Instead of it being endless metadata, it's just, it's 1 byte every 30 seconds, so that effectively it never finishes. Again, this is a kind of UI issue. If the user interface is blocking while you're doing an update, you as a user are going to notice that it's taking hours, but if it's happening in the background, you might not notice. So it has to be, these are possible attacks. So, it's worth noting always that if you sit in the network between the client and the server, you can always prevent an update, right? But it should never be the case that you can prevent an update without the client noticing, right? That's, okay, so which of these attacks do our naive approaches cover? Surprisingly few. So if authors sign packages, well, we've got the modified tarballs one, but really none of the others. And the wrong author one is only dealt with if we're careful about how we decide which keys to trust. If we just have this set of keys that we trust, then they can upload any of them, right? If I trust, well, let me not name names. So I'm being generous on the wrong author one. You could easily miss that one out as well. Okay, server signs a manifest, hardly does any better. Actually, let me just quickly, why did this not get these other ones? The key thing with signing packages individually is that there's nothing that ties them all together. So rollback is easy because, well, I can just supply you with any collection of packages so long as individually they're all signed by someone. But that means I could supply old ones, I could always supply the same ones, I could supply arbitrary combinations. There's nothing that ties them all together and says this set of things existed all at one time and you can't ratchet backwards or something. If you're just signing everything individually, there's nothing that ties them together, and all these rollback frees and mix and match are all possible. Extra dependencies I've said there because if you look at Hackage, we distribute the cabal files separately from the tarballs. And if you're not securing those, then that's a trivial way to, you would have to also secure the cabal files as well. And I didn't say that in my first one, so it would be vulnerable to that. Server signing a manifest only does slightly better. It does prevent mix and match attacks because you're signing the collection as a whole. You can't take combinations that never existed because that has not been signed by the server. But it's still vulnerable to rollback and freeze attacks because we didn't do anything to stop that, basically. And again, you could prevent the extra dependencies ones provided that the manifest also lists those extra metadata files. It lists the cabal files, their hashes as well. But I only specified at the beginning that we would do the tarballs, and so it would be vulnerable to extra dependencies attack as well. It's not vulnerable to the wrong author ones because we're assuming here about an attacker between the server and the client, and if the server enforces the wrong author, who can upload what, then the fact that the manifest lists everything as a whole means that you can't do that attack. So that one's sort of okay. HTTPS does quite well on these, which is perhaps not so surprising. Ooh, blimey. I need to get a move on. Okay, I'm going to skip HTTPS because it's not interesting because it doesn't do mirrors. Okay, tough. So it's an existing architecture. It's written by a bunch of academics. It's an architecture and an implementation, but we're using it as the architecture. and it's somewhat adaptable to fit different use cases. And it basically uses a combination of the things we saw already. It uses server-based manifest signing, index signing, and author signing, and some extra bits to deal with replay, freeze, and download attacks. And so it identifies all these attacks and has measures to prevent all of them. And it has a single, coherent, and modular design. There's a bunch of papers. I'm not going to go into the details of how tough works, actually, because I don't have time, except to say that different keys live in different places. Some keys can be held offline, some keys have to be online, and so a compromise of one doesn't necessarily bring down the entire system. It's agnostic about what signatures and algorithms you use, so it recommends SHA-256 and ED25519, but it's extensible over time, and those are in fact the ones that we use as well in our implementation. We adapt this architecture for hackage, so it's not exactly as the tough authors have specified it, but it's a sufficiently flexible architecture that we can specialize it to hackage. And so we've made some changes to it to fit better with how hackage already works, to keep it backwards compatible. I hadn't realized how long I was taking, so I'm going to skip talking about that in detail. We're doing this in 2 phases, and the modularity of TUF allows us to do it in phases. The first phase does not include author signing. It includes index signing. So it means that it's all fully automatic. Phase 2, if we can get funding for phase 2, also includes author signing. Yeah, so that means it's still vulnerable if the server itself is compromised. And phase 2, adding author signing, would add extra protection for those packages that are signed. There's a hackage-security library, which this whole thing uses. This is used by clients like cabal-install, or Stack could use it. It implements the procedure for talking to the repository over HTTP. It makes use of mirrors. There's also some other... I'm not going to talk about that. I'm not going to talk about that either. So that we're now using it in cabal-install. There's a patch available, and there's a beta available now for cabal-install that uses the library, and we will bundle, if necessary, the library and an ED2519 and SHA library with cabal-install, if necessary, to make that work. I think it's important that these things are really baked into, as libraries baked into the cabal-install tool, or indeed any other tool, because it means that you don't have problems with environment and configuration that can cause it to go wrong. And this is important because this is going to be always on. It has to always work. So it would be annoying to rely on external tools where in some small proportion of cases it will just not work and cause endless problems on the IRC channel for everyone trying to support users. It's also implemented on the server. We've got mirrors and automatic mirrors, but I don't have time to talk about that. So let me talk about the current status, because I'm basically out of time. Okay. So we had an alpha release a few weeks ago. We've got a beta release out right now. It's easy to try it out. You just cabal-install these tarbles. That's also on a blog post, and I'll make this available as well. So there's a beta announcement which has these links. It's already deployed now on the central hackage server. All the extra metadata files that are necessary to make this work are already there. The library's all released, and there's also a live mirror available. There's a few things left to do. There's a few known issues we have. We've got to fix anything that comes up from during the beta, and the details of key management we have to resolve. Hopefully we can do that this week. I won't go into the details here, but we will basically have the Haskell.org committee be the kind of root of trust, and they'll hold the keys, plus delegate them to a few other people. But we have to nail down exactly what the procedures are for updating and re-signing. And so there's a few details to hammer out, but hopefully we can do that this week, and possibly even create some new root keys and get those. Right. So that'd be good. Right, so I'm basically done. Thanks to the IHG for funding this, the members of the Industrial Hassle Group. The Oregon State University's Open Source Lab are hosting a mirror for us. My colleague Edsko wrote almost all of the code, which is very nice. Lots of types, it's beautiful. And thanks to feedback from people who took part in the alpha test, particularly Herbert, for lots and lots of feedback. And that's it. Sorry, I went into too much detail at the beginning. Anyway, thank you. And if you have possibly time for one question, or... Okay.
Does this rely on getting an initial key out of the user, say a key from
So the clients, like cabal-install or stack or whatever, have to be distributed, pre-distributed with the keys for hackage. So they have to be given the key hashes of the root keys, the public keys. So yes, they have to be distributed with those, which does create an interesting bootstrapping problem. But which is one of the things you have to deal with when deciding what your policies are for rolling over root keys over time, etc. Because old clients have to be able to bootstrap. But no, by default, it's fully automatic. The client is distributed with the root keys, and so it can bootstrap automatically. If you want to create your own repository, you've got to give your clients the root keys. So there's a little bit of extra configuration you've got to put into your cabal configuration file to use that server if it's a non-standard, not the central one that has been distributed with. Yeah. No question? They're simply held in memory. Yeah. And those are only for certain keys. Like the root keys are all offline, but it's the timestamp and snapshot keys which are used regularly to re-sign something. In a similar way to like an HTTPS server, typically just holds its private keys in memory. Not particular, but pull requests are most welcome. There's a question over here. Yeah? Yeah?
So, since you took that, you were mentioned developed by a bunch of academics, and it is security, so it's important to get all the details right?
Yeah.
What are the methodology or the ideas that you have to know that the code that you are implementing, or a bunch of people are implementing, really fulfill with the ideas of that, and not the adaptation that you, or modification you're going to introduce because it's working package or
Yeah. How do we know we're doing that right? Yeah. No, it's a very good question. I mean, so we try and make our implementation as simple as possible and correspond as closely to the specification as possible. So you can read, the bit that does the update is like this long, and then the spec it's like this long, and we try and do it exactly the same. So it's by using the advantages of Haskell to make things as simple and clear as possible, by using types to their full advantage to enforce separation between trusted and untrusted data, that kind of thing. But otherwise, no, and we have to rely on, code review and because it's hard to test for security things. It's hard to test for vulnerabilities, right? Possibly, we haven't done so. But we certainly welcome review from other people, both of the code and of the adaptations that we've made. I'm afraid I didn't have time to go into all those, but anyone who's interested is very much welcome to go and look or talk to us, and we really welcome review. Yeah. Okay. All right. Thank you very much.